the chemical equilibrium composition. We'll do that first, and then we'll get to the phase equilibrium. You have an equation for the equilibrium of a reaction. So not everything goes from reactants to products like we did for combustion. Combustion is so lopsided that basically everything goes that way for heat release calculations and a lot of calculations. Now, if you're really interested in parts per million of something like nitrogen dissociating or creating nitrogen dioxide, then you would deal with you wouldn't consider it going all the way, and you'd have an equilibrium equation for that composition. The theory in developing the equilibrium equations are in the textbook, so I'll just gloss over this. I think I spent more time in it, but basically we had temperature equilibrium, thermal balance. We had force and pressure for mechanical, and here we have composition balance. So it's an equilibrium composition. So what's in equilibrium? It's something like a chemical potential. Okay, just like a temperature potential and a force potential. So there's a first law, you rewrite it, you take the second law, you combine them, and you find that for all real processes where you have entropy production, that this grouping of terms doesn't look physical at all, does it? TdS minus du minus P dV must be greater than or equal to 0. We consider fixed temperature and fixed pressure. If you change the temperature, you change the equilibrium composition. If you change the pressure, you change the equilibrium composition. But our goal typically is to say, this is a given pressure, this is a given temperature, you calculate the equilibrium composition. That's why they're fixing temperature and pressure in the discussion. You introduced or recall the Gibbs function by this grouping of properties, do a little calculus for a differential. We then look at the grouping of terms. We say, hey, that's the same as this over here. Because it's a negative sign, we switch to inequality and apply it to the left-hand side of that equation. We say that this grouping of terms must be less than or equal to 0. If there's no change in pressure, no change in temperature, then dG must be less than or equal to 0. And that's our equilibrium criterion. It doesn't look all that special nor insightful, but the Gibbs function, if you're not, it goes to a minimum at equilibrium. If you're not at equilibrium, it will go toward equilibrium and decrease in G. Either you're to this side or that side, but it'll go to a minimum in the Gibbs function. We apply this now for a single-phase multi-component system. What does the Gibbs function look like? Well, in general, it's a function of pressure, temperature, and then the compositions of all of the components. We can put those compositions in just n, the number of moles. And then you say, well, G then, there's a few steps I left out right here, but G is equal to or can be computed by for the mixture as the components, how much is of each of the components, times the partial of G with respect to that component's concentration or composition. This is a funny subscript. It's really hard to see in the textbook, but that's an L. In a lot of instructions for authors, and they say never use L as a subscript. Just take it off. Why? Because it looks like 1. And so it's really a bad subscript. Never use L as a subscript. It's too easy to be confused. So that's the general rule in technical writing. The textbook introduces chemical potential, which is that derivative of interest, mu, and we find that then the Gibbs function is just the sum of mu's times ni. So at equilibrium, recall the equilibrium criteria, that dG is equal to mu dNs. Let me see how to calculate the G for an ideal gas mixture, combination of H's and S's on a molar basis. So there you go. So there's a molar Gibbs function. There's a few, that's what makes this hard. There's a few new definitions, and we don't have time to really spend a whole semester on it. But the Gibbs function on a molar basis. And now we have the ideal gas, how to calculate it. This mu's So the chemical potential is the same as the molar Gibbs function. Mu sub I is equal to G sub I. This is the expanded equation, emphasizing that this HI is a function of temperature and the SI, the entropy and the enthalpy, are functions of temperature. Okay, and so it simplifies for an ideal gas. Here, notice, well, they introduce another parameter. It's just G bar naught for that component. All right, so take a chemical dissociation reaction equation. Here you start with the component A, B, and it goes into some sort of, at equilibrium, it can be continually exchanging, but now you have an equilibrium mixture of A, B, C, and D. So this is the general case where you have 4 components. You can have 3 components, and you can even have 2 components, but 4 is the general case that you may have seen in your textbook. Here's a case with 2 of them. H2 dissociates to 2 H's. Dissociation of hydrogen. Let's do one with 3 components. CO2 dissociates to CO plus 1/2 O2. That's a dissociation of carbon dioxide. And then there's other examples where you have 4 components. But that's what these A's stand for. That'd be like H2. Nothing for B in this first example. C would be H. And the coefficient, the stoichiometric coefficient in front of H is 2. Where the stoichiometric coefficient in front of H2 is 1. So hopefully all of that makes sense. How many people have seen and analyzed, recall this type of equation from chemistry? Not all the hands are up. Most of the hands are up. Why aren't all the hands up?
Didn't we use this with like KQ?
K what?
So the K constant of equilibrium.
That's exactly where we're going. You've got it right here. This is the equilibrium constant K. It's a function of temperature only. And then we isolate. So this is our bottom line equation for chemical equilibrium. We have K, equilibrium constant, function of temperature only. And on the right-hand side, we have isolated the compositions as well as the pressure effect. Well, okay. Taking a look at this general equation and how you can apply it for a few cases, then what you do is think about moving the reaction going from the left side to the right side. And so this extent of reaction, if it moved forward, you would have a decrease in the amount of A. You'd have a decrease in the amount of B. And it would be related to the stoichiometric coefficients. Maybe these equations are very, very similar. So think about the extent of the reaction, d epsilon. So it would be subtract the stoichiometric coefficient of A times d epsilon. All right. So you put these into that Gibbs, the function for equilibrium, and you then bring in that it must be an ideal gas mixture, and we're getting to this equation right here. You collect terms which are temperature dependent. All these terms on the left-hand side are a function of temperature. And you leave the pressure to the right-hand side. Actually, you bring the RT over as well. So you get delta G naught over RT. And you say, hey, we're going to introduce now let me see. Take the, okay, then you have the natural log. You use some of the rules of combining with natural log. So you get all the mole fractions, the pressure, the ratios, the powers of the stoichiometric coefficient. And then you take a look, you say this left-hand side we're going to define as the log of K, which is a function of temperature only. Now that we have log is equal to log, you can exponentiate both sides and you find the equation. K is a function of temperature only is equal to this ratio of mole fractions, each to their individual stoichiometric coefficient, raised to that power. And then P over P ref, reference pressure, 1 atm. Sometimes you have to look through the book and say, well, what is the reference pressure? It's 1 atm. 1 atm, 1 atm, 1 atm, 1 atm. And they often give the pressure in ATMs. So you'll just see, oh, it's 3 atm divided by 1 atm. They'll just put 3 in there. You say, what? Yep, that's what you have to follow. So this is 1 atm. All right. And then this is all the coefficients. Now, how many remember using this type of equation? Some of you? No, but not all? Well, you got to review it then. Okay? Please review it. You can write it in terms of mole fractions, or you can write it in terms of amount n, where n sub c is, or n sub c divided by the total number n is equal to y sub c, the mole fraction for the ideal gas mixture. As written right here, these are for ideal gas mixtures. All right? All right. Here is where you get the equilibrium constants out of the table for select reactions. Dissociation of hydrogen, dissociation of oxygen, etc. Notice that they're a function of temperature, and it's traditional or common to write it such that at low temperatures it likes to stay to the left. How is that shown? By large negative numbers. Large negative numbers, large negative numbers, large negative numbers. And as the temperature increases, what happens to the size of this? What they're putting in here is log base 10 of K, that equilibrium constant. It goes and increases from a large negative number up towards 0, and then it can even become positive as shown here. Oops. As shown here, true? It's positive. So that can be negative or positive, but it's common to put it where it starts large negative at low temperatures. As temperature increases, it increases. So what happens is you can look at the magnitude and say, you know what, there's very little dissociation. And then, oops, now we're starting to get some. You know what? Now it's even positive. We're getting a lot of the stuff that's going to be on the right-hand side. It's not going to be on the left-hand side. It's going to be on the right-hand side of that equation. Okay. We're going to solve a problem, and we're going to solve it for, I think it's 1900 Kelvin. That's a temperature. And I think we're going to do it for this problem. Maybe not. Maybe I'll look at the problem and come back. So take a look at 1900 Kelvin for this reaction equation. That reaction equation is water dissociating. It's hard for me to draw this arrow going back and forth, right? But that's what I'm trying to draw there without being a good expert at word processing. H2 plus 1/2 O2. Let's go back and take a look. H2 plus 1/2 O2. Isn't that the right reaction or dissociation? So they ask us, they say, in our problem, from the data in the table, determine log base 10 of K for that reaction. So for this reaction, log base 10 of K is equal to, did I get that right at 1900? Negative 4.190. Oops. Is it H plus half O2? Oh, thank you, thank you, thank you. It's so easy to make a mistake, isn't it? And then when you're trying to grade all the students' exams, you're saying, where did they get that number? And then you go, oh, well, if they would have just grabbed the number from one column over. Now, did they finish it the rest of the way correctly? Only way sometimes to find out is to run the numbers myself. Oh, it takes me a long time to grade exams. Sometimes I just give up. I can't find your error. You find it for me, please. Otherwise, I just take off a lot of points and then, let you come back to me and show me where your error was, because sometimes it can take days to grade exams. And I don't have days, right? I want to get it back to you so you know how you did. Okay, thank you for helping me get the right number. So it's negative 3.886. So easy to mess up, isn't it? 3.886. Okay. So that was just going to the table and reading it. Now they say, not that reaction, this reaction. So take a good look at this reaction. And what you'll do is it doesn't look as well typed out, but the first one is H2O dissociating to H2 plus 1/2 O2, right? Water likes to stay together at low temperatures, but if you get it hot, it'll come apart. And then that hydrogen will collect it as a gas at the top. You'll take it off, and you just produced hydrogen. How do you produce hydrogen? Breaking up water. Electrolysis. Do it with electric current. You can break it up like that too. All right, this is thermal dissociation. Now, what about this reaction? They say, no, we're starting with hydrogen, and we have 1/2 O2, and somehow it reacts to get to H2O. Well, you can look in the table all you want, but you won't find that reaction. It's switched, isn't it? Isn't what was on the left is now on the right, and so if you switch them, you'll get back to the equation that you know already about. True? So how do I get and infer a log base 10 of K, the equilibrium constant, for this new problem, part B? Well, one thing you can do is take a look at our general reaction equation and just write it down for the first case. The first case was that this nu sub A was 1. This was H2O. This is all 0. This associates to hydrogen with a 1 coefficient and 1/2 on O2. True? Write it now for our new equation, and we're going to say nu sub A is 1 times H2 plus 1/2 O2. This associates to become 1 H2O. True? And we're interested in calculating K2, the second equation K. We're probably going to be able to relate it to K1, the first equation K. That makes sense on the subscripts, K1 and K2? Okay. If you look over here, K1 was equal to y sub c, y of H2 raised to the exponent 1 times y sub d, d was O2, raised to the exponent 1/2 divided by y of A, which is H2O, raised to the exponent 1 times the total pressure over 1 atm raised to the power nu sub c 1 plus nu sub d 1/2 minus nu sub A 1. True? That makes sense? Okay, let's take a look at K2. K2. Well, is it going to be y sub H2O to the 1 power divided by y of H2 to the 1 power, y of O2 to the 1/2 power, and then you have P over 1 atm to the 1 minus 1 minus 1/2. True? What was, if I simplify this, what does that simplify to? Positive 1/2. If I simplify this, this simplifies to negative 1/2. True? So can you see the relationship between the K's? What is it? K2 is equal to 1 over K1. Is that right? How many people agree? Now on a log basis, if I take the log of, let me do this, leave a little room, 1 over K1. If I take the log base 10 of both sides, is that equation still true? Sure. So the log base 10 of K2, what I really want for the new reaction for part B is equal to log base 10 of 1 over K1, which is negative log 10 of K1. So if I want to calculate log base 10 of the reaction for B, it's equal to minus a minus. Make sense? So if you switch the equation around, the log base 10 of that K switches sign. True? Good. All right, let's take a look at this equation now. We have 2H2O goes to 2H2s plus O2. Well, I compare it with my original equation, right? What did they do between the original equation and this equation for part C? They multiplied it by 2, the whole equation by 2. So I suspect I'll do something with this K of 1, but let's work it out, okay? So think about this reaction equation be log of K3. How's that? Or K3. So K3 will be equal to Y of H2, but now Y of H2 is to the exponent power 2 because that's the stoichiometric coefficient in front of the hydrogen, times Y of O2, but not to a half now, it's to 1, divided by Y of H2O to the power 2, P over 1 to the power, not a half, but it'll be 2 plus 1 minus 2, it'll be 1. So I compare this equation with this equation, and I see what is the relationship between K1 and K3. Is K3 equal to K1 squared? I have one yes, a couple more yeses. Yes. Now they ask me, what is the log base 10? So I take the log of both sides of this equation. I get log of the new equilibrium constant is equal to 2 times the log of the previous equilibrium constant. So log base 10 of K for the third reaction equation is equal to negative 7.772. 2 times. True? So that's what happened. Make sense? So we're done with that one. Ready to move on? Here's a long problem. So it'll probably take the rest of the time, but we'll get to it. A mixture of 28 kilomoles of CO2 and 2 kilomoles of hydrogen and 2 kilomoles of carbon monoxide and 28 kilomoles of water vapor and 40 kilomoles of nitrogen enter a heat exchanger. Well, the heat exchanger is going to make it hot and then also give it some time to react. An equilibrium mixture of the same components, CO2, H2, CO, H2O, and N2, exit at an elevated temperature of 1900 Kelvin and 1 atm. Determine the equilibrium composition of the exiting mixture. So we know what went into the heat exchanger, and what comes out is an equilibrium mixture at a given temperature of 1900 Kelvin and pressure of 1 atm. And we're asked to calculate that composition of the equilibrium mixture. It's a very different problem than the ones you've been solving so far. All right? So we take a look at all the players. The players are carbon dioxide, hydrogen, carbon monoxide, water, nitrogen. Now, I count them up, there's 5 of them. The maximum equation we had A, B, C, D, that's 4, right? So one of these are what they call inert. It's not doing anything, it's going along for the ride. Now if you change it to temperature, really boost up the temperature, they may say that one's now going to start participating and starting to do something by decomposing and recombining. But in this stage, you almost just have to know that the nitrogen is inert. And the other ones are the ones that are doing something. The carbon in the CO2 is dissociating and going to CO. And some of that H2, that hydrogen, is working, playing around with the H in the water, H2O. And the oxygen's in the carbon dioxide, the carbon monoxide, and the water. But nitrogen's only by itself. True? Did they say any NO? No, they didn't. If they did say NO, then we would have a much different, more challenging problem. But at this point, N2 is inert by itself. It doesn't react. So if you came in with 40 kilomoles of N2 in the equilibrium mixture, how many kilomoles of N2 do you think you're going to get? 40. If you came in with 40 kilomoles in the equilibrium mixture, you have 40 kilomoles. Now you could do 40 kilomoles per second or something, so it's more of a flow problem. But it's easier to get rid of the per second, just talk about it's 40 kilomoles in the equilibrium mixture of nitrogen. All right. We go back and we look for some reaction equation of this form, A, B, C, D, which describes carbon dioxide, hydrogen going with carbon monoxide and water. And do we find one? I think we do, but you have to just go looking for it. Is it this one? This is the only one that has 4 players in it, isn't it? This has 3 players, 3 players, 3 players, 3 players, 2 players, 2 players, 2 players in it, right? But this one has 4 players in it, and it's the one we need. I'm glad because we only have one table of dissociation reaction equations or equilibrium constants. So it said it was 1900 to temperature. And so this number right here is log base 10 of K is equal to plus 0.619 for this reaction. CO2 plus H2 goes to CO and H2O. Back and forth, it's a dissociation. So let me go and leave this page, but you'll have to remember this number. So the equation of interest was CO2 plus H2 dissociates or combines in an equilibrium mixture to have CO and H2O. And it's really important to get those coefficients in front of each term. And I believe every one of those were 1. Every one of those stoichiometric coefficients were 1. We look at that equation, let's just check. Does the carbon balance? Does the oxygen? Yes, hydrogen? Everything's balanced. It's a good reaction equation, right? So there you go. We want to compute the equilibrium composition. This equation applies only at equilibrium. That's our chemical equilibrium equation. Here we put it in terms of n's. Sometimes you use this form or the y form, the mole fractions, because they told you the total number of moles, like 28 kilomoles of CO2, etc. Then let's just use this. So what we have is we're going to have the 10 to the power, what was the coefficient? 0.619, right? 10 to the power 0.619, that's what K is at this temperature for that reaction, to the number of moles of C. That's going to be the number of moles of carbon monoxide. Carbon monoxide's in that C position, raised to the power 1. Number of moles of H2O, because water vapor is in the D position, raised to the stoichiometric coefficient 1, divided by number of moles of CO2, which is in the A position, raised to 1, number of moles of H2, hydrogen, raised to the coefficient 1. We have P divided by 1 atm, divided by the total number of moles, which is the number of moles of carbon monoxide, number of moles of water, number of moles of carbon dioxide, and the number of moles of hydrogen, plus the number of moles of nitrogen. All of them make up your gas at equilibrium, even though the nitrogen's inert. Even though the nitrogen's inert, it still needs to be, it's in the total N. All raised to the power, we're going to have 1 plus 1 minus 1 minus 1. Now, this is a very special case, and how many people already realize that this exponent up here is 0? 1 plus 1 minus 1 minus 1, right? And so all of this right here is equal to unity. You know, any number raised to the power 0 is 1. True? From math. So our equation simplifies, and so it's just 10 to the plus 0.619 is equal to the number of moles of CO times the number of moles of H2O in equilibrium, number of moles of CO2 in equilibrium, number of moles of hydrogen in equilibrium. That's it. That's our equilibrium equation. I don't know 4 things in that equation. I don't know any of the n's. True? I need other equations. This equation is an equilibrium equation. There's other equations which are mass balance or species balance equations. So if we go and we say, can I write a carbon balance equation? What would that look like? Well, they told me I had 28 kilomoles of CO2 coming into the heat exchanger, 2 kilomoles of hydrogen going into the heat exchanger, 2 kilomoles of carbon monoxide into the heat exchanger, 28 kilomoles of H2O going into the heat exchanger, and then 40 kilomoles of N2. I didn't really sum them, but if you sum them, can you see that you get 100 kilomoles in? 28 and 2, that's 30. 28 and 2, that's 30, plus 40. So you have 100 kilomoles coming in. That's nice numbers. Makes it easy to do the math. But on the carbon balance, we're going to have 1 for every of the 28 kilomoles of CO2. That's bringing with it 1 kilomole of carbon. And we're going to have 1 for every kilomole of CO that comes in. And there's 2 that come in of the CO. So in total, what comes in is 28 is 30. What goes out? Well, in every CO going out, which I don't know the number of, that's an unknown, I need to calculate that, I'll have 1. And for every CO2 that goes out, I'll have 1. So there's an equation. It comes from a carbon balance that says 30 is equal to, in equilibrium, the number of moles of CO in equilibrium plus the number of moles of CO2. Let's do the next balance. What balance do you want to do? Oxygen? Okay, let's count them up. I had 28 kilomoles of CO2 coming in. For every CO2 coming in, that's bringing with it 2 O's. How many with the hydrogen? Nothing. How much with the carbon monoxide? Well, I had 2 kilomoles of carbon monoxide coming in, bringing with it 1 for every 1. And do I have any oxygen with the water? Yes. So we had 28 kilomoles of the water, H2O, and for every 1 is 1 coming in. True? That's all the N. That's the oxygen balance on the N. And when you sum that up, you get 86. Okay? 86. Now, how much going out in equilibrium? Well, we'll have 2 for every CO2. We'll have 1 for every CO. and we'll have 1 for every H2O. Does that equation look okay? So 2, I can maybe rearrange it and put NCO plus 2 NCO2 plus NH2O. Let's clean it up a little bit. So now I have an equilibrium equation, I have a carbon balance equation, oxygen balance equation, 3 equations, but I still have 4 unknowns. I need one more balance equation. What is it? Hydrogen balance. So with the hydrogen balance, we see that we have 2 times the 2 kilomoles of hydrogen coming in, and we have 2 times the 28 kilomoles of water coming in. That sums up to 60. And going out, the hydrogens, we have 2 times number of H2 plus 2 times the number of H2O. Does that hydrogen balance equation look good? Ooh, did I tell you that I used this on the final exam 1 year ago? Yeah, this was on the final exam 1 year ago, this problem. So, there you go. So now I have 2 times the number of H2s plus 2 times the number of H2Os. Now, what you can do is you can either solve 4 equations and 4 unknowns where one of the equations is nonlinear, the equilibrium equation, or what you can do is try to eliminate variables and push them into that one equation and get the one equation, one unknown, which is your nonlinear equation with your equilibrium. That's the preferred strategy. It's what's done in the textbook. So you just pick one, and so pick to solve for NCO and then get every other thing in terms of it. So from the carbon balance equation, wherever you see a CO2, replace it by 30 minus NCO. Does that make sense? Any place I see a CO2, the number CO2, I say, replace it by 30 times NCO. So if I start reworking this equation, I'll leave NCO right there because that's the one I picked as my variable I'm going to solve for. But right below it, I'm going to have 30 minus NCO. That was the easy one. Unfortunately, it gets a little uglier because I've got to work out this NH2O and the NH2. Let's go to the second equilibrium equation, this one. Okay? So this one says, I'm going to kind of do it in multiple steps. N of H2O is going to be 86 minus N of CO minus 2 times N of CO2, right? But any place I see an N of CO2, I replace it by 30 minus N of CO. True? So this becomes not just 86, it becomes 26 plus NCO. So the number of H2O is 26 plus NCO. So I come up here, 26 plus NCO. Now, guess what you do for this equation? Same thing. All right, I need to solve for the number of H2. Is that going to be 30 minus the number H2O? Thumbs up if you agree. So that's equal to 30 minus 26 plus NCO. True? Which is 4 minus NCO. So now I have reduced it to one equation. I need more room, so I'm going to have to scroll down, okay? So I scroll down, and I have this equation. 10 to the plus 0.619 is equal to what I'm looking for, NCO times 26 plus the number of carbon monoxide divided by 30 minus the number of carbon monoxide times 4 minus the number of carbon monoxide. One equation, it's nonlinear. It's still algebraic, but it's nonlinear with one unknown. How are you going to solve it? On a final exam. Professor didn't let me bring in Excel. He won't let me go out to the internet. You have to have a calculator. And you have to know how to solve for that. So, learn how to do that. Do it now, right? And a lot of you, when I teach this class, always there's some people that are like, hey, before I can start to, encourage students to do it, they already have the solution. They pop, 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 right? So when you have this equation, you have to be able to solve for and solve that N of CO is equal to 3.17. That's the answer. It has units, kilomole. And once I have that from this equation, then I can go back to each of these previous equations, calculate NCO2. That's going to be 26.83 kilomoles. The N of H2 comes in at 0.83 kilomoles. And the number of moles of H2O is 29.17 kilomoles. And the number of moles of N2, nitrogen, going along for the ride is still 40 kilomoles. And if you wanted to, that would be acceptable, just leave it in the total amounts. But if you wanted to calculate the mole fraction of CO, you just sum up all of these. You find out that the sum is 100 kilomoles. Again, good to 4 digits. And so then this just becomes 3.17%. This becomes 26.83%, etc. Because it's all 1 kilomole. 100 kilomoles total number of gas. Okay, so the mole fractions for this problem, because I started with a nice number N coming in, is equivalent. So Y of H2O is 0.83%, etc. 29.17%, and Y of N2, 40%. That's the answer.